Hi everyone, and welcome to the first of our pre-recorded video lectures for NRES 470-670 Applied Population Ecology. This is spring 2021, and we are still in the midst of a pandemic at the moment, so we're making the best of the situation. We're online, obviously, and so we're going to try some new things, and this is part of it, having these little brief pre-recorded lectures as supplements, and we'll explain today why we're doing this. The main reason is because of, this is a modeling class basically, and the more hands-on we can get with modeling populations using software like R and Insight Maker that we're going to be using throughout the class requires, really the only way to learn it is hands-on. And so in class, we're going to devote most of the time to working in groups or individually doing hands-on activities, which leaves the lectures for outside the class. So this is what we're doing, and this is why we're here. And so we should have gone over the basics of the class before you watch this lecture. We'll go over that on Monday. I'm recording this on Sunday, the 24th of January. So I will see you all tomorrow, and we'll go over the basics. So I'm going to skip over that. Here's the class website. This is kevintshoemaker.github.io/NRES/470. That's the class website. This is the home page. And we're going to skip right over to this lecture under the lectures tab here, where it says a whole systems approach to population ecology. And I like to start, this is kind of the first of the actual lectures in the class, and I like to start here, even though this class is not really a systems ecology class. This is a population ecology class, but I like to start with the systems diagram that goes through. This one happens to go through the carbon cycle in an ecosystem, but it really could go through any sort of complex ecosystem process. And what I'd like to show here is just how many connections there are in a real world ecosystem. Ecosystems are complicated. Natural systems are just complicated and full of interconnections, and that's really what makes it interesting to study these kind of systems. But it's also what can make it kind of frustrating, because we as humans have our limitations in terms of how much we can stuff into our head and actually understand. When we start to think about all these different arrows and how these relationships work between these different species, and how this all goes together to potentially produce ecosystem level processes like carbon flux. In the case of this class, we're going to talk about population dynamics and metapopulation dynamics. That is the dynamics of many populations going extinct or being recolonized, and how many populations are colonized at any one time. Looking at these big picture processes can be difficult, and it's not something we can do just by looking at a diagram like this and being like, oh, now I know how this all works. It just looks complicated and daunting maybe. And what we're going to do in this class is try to put numbers and relationships on these types of arrows. And even though we are not so great as humans at putting this all together, what is great at putting this all together? Computers, obviously. And we have really good high-powered computers at our fingertips. And so we're going to be doing computer modeling of systems like this because computers help us understand complex systems. We are good at drawing diagrams like this and trying to understand what these arrows represent and how and what sort of equations might be represented by this relationship between this songbird and this grasshopper. And we can put that one relationship, and we can try to think about that one relationship and figure out how that relationship works. But a computer is going to help us figure out, once we put all these arrows in here, to figure out what the implications are, what's going to happen in the system. So that is just a brief overview. That's why I kind of like to start with this diagram, because it just illustrates how complex ecosystems are, how interesting they are, and how much it helps us to use computers to help us model these systems and understand what the implications of all these arrows are, all this complexity is. So that's where we're going in this class. We are going to move fairly slowly. I know a lot of you are new to computer programming. A lot of you have not used any computer programming before, and I understand that. And so we're going to go real slow, and that's part of the reason we're going to take a lot of class time this semester to go over the basics of modeling and to walk you through it and give you a chance to ask lots of questions and stuff like that. So that's where we're going. I'm excited to get started. I hope you're excited to get started. I find, I don't know, maybe this is just me, maybe I'm weird, but I find that modeling ecosystems is incredibly fun and exciting. And the fact that these models can have real important impacts to conservation and wildlife management makes it even more exciting, because it's not only fun, but it's really useful, and it's becoming more and more useful as our models and our understanding of ecosystems gets more and more complicated. So yes, it can be kind of daunting, but think of it as an adventure. So that's where we're going. One of the really important points that comes out of systems thinking, that's what we're talking about here, thinking about these complex systems and using computers to help us understand these complex systems. And one of the most important concepts that comes out of systems thinking in general, and you can read more about this in chapter 1 of the interactive textbook, Beyond Connecting the Dots. The link is in Web Campus and in Top Hat. So please download or use the web version of Beyond Connecting the Dots and read chapter 1, which is all about systems thinking. So one of the most important concepts is emergent properties. So, and the idea of emergent properties is that when you put many interacting linked parts together, systems often behave in interesting and unexpected ways. And that is, you can put really simple relationships on any of these arrows. For instance, the more food resources there are for a consumer, then the more there's a linear relationship. The more resources, the more births for that consumer, and that's a linear relationship, very simple. And you can put equally simple relationships on all of these arrows, essentially. And then when you run the model, you might see something weird happen. You might see oscillating patterns. You might see a non-linear relationship. You might see a threshold beyond which the population crashes, and you did not put that in the model. The model consists of really simple relationships, but as a system, you see very interesting behavior at the higher level. For instance, this ecosystem model, you might see some pattern in the carbon cycle relationship that you just would never have expected by just looking at the simple relationships you put into the model. So that's the idea of emergent properties. And let's look at an example of an emergent property. This is a example coming from Insight Maker, the tool that we're going to be using a lot in this semester. And this is the classic example of the snowshoe hare and the lynx from Canada. And this is a relationship that's in all the basic ecology textbooks, and you kind of probably already know what this relationship ends up looking like. But it's kind of interesting to look at how simple the relationships are that go into this model. For instance, the death rate of the snowshoe hare is just a proportion of the number of lynx in the landscape. That's a really simple relationship that describes the predator-prey relationship. And you can look at the birth rate of lynx as well, and you can see that the birth rate of lynx is just a proportion of the total number of snowshoe hare that are out in the landscape. So it's super simple. And everything else is just very simple as well. You have a constant birth rate here, And you see here that you just multiply the total number of snowshoe hare that are out there with the birth rate to get the total number of new births in the population. That's really simple. And to look at the death of lynx, you can see that there's a constant death rate, and you just multiply that death rate by the total number of lynx, and you get the total number that die every year. Really, really simple. You have all these simple relationships, and yet when you run the model, you see that we get this oscillatory pattern. That's an emergent property. It's an emergent property because there is no nonlinear pattern in any of these arrows. There's just very, very simple relationships. We didn't program in an oscillation. That just happened naturally out of this system. Even this relatively simple system with only 2 species, we have this interesting, complex, unexpected pattern of an oscillation abundance going from high to low abundance over time and repeating over and over at every certain number of years. That's an unexpected relationship if you just look at these connections. They're very simple. All right. And just one more example of an emergent property. This one isn't from ecology at all. This is from systems dynamics and in mathematics, but it is kind of interesting just to look at because we can again see a really it's a relatively simple system here that ends up with some fairly complex emergent properties. And so we have 3 stalks called X, Y, and Z, and we have these parameters that are just numbers basically, and then you have these really simple equations that relate the stalks X, Y, and Z to one another via these parameters. But these are really simple relationships. If you just look at them, there's nothing really complex mathematically about these relationships. We're not coding anything weird here. We're not doing anything weird. We're not putting any weird nonlinear. We're not even putting square roots, or we're not putting exponents on them or anything. There's nothing that complicated. And yet, when we simulate it, first of all, this is just looking at the variable y, or the stalk y over time. This looks a little weird. It looks a little random, right? But then you can start to look at if you look at the X stalk and the Y stalk at the same time, so this point represents a particular point in time. There was this amount in the X stalk and this amount in the Z stalk, for instance. And we start to see these really complex patterns emerge. And you can look at the other planes as well and just see these really interesting, complex patterns that you would never expect based on these simple relationships that you see here. So emergent properties can be really cool and exciting, part of modeling systems. And so it's something to be aware of when you're modeling your final project system, doing your population viability analysis with a species that you're interested in. You're likely to find some emergent properties in that system as well. And it can be a really, really exciting thing to see because by definition, emergent properties are unexpected. Right. So that's the idea of an emergent property, and we'll have plenty of chances to really explore emergent properties more in the class. Just a few words about Insight Maker, the tool we're going to be using. Hopefully, we're going to have more experience working with Insight Maker in class on Wednesday. That'll be the primary focus on Wednesday, is just going through very slowly, introducing you to the tool. So I'm not going to go through great detail here, but I just wanted to say a few words. It really is a powerful programming language for modeling systems. I like to think of Insight Maker as kind of a sneaky programming language because although it is a powerful programming language, it's also super easy to use. And so it's easy to forget that you're working with a programming language here. And finally, just a few words about computer programming and systems thinking. I've already talked about why computers are so important for modeling complex systems. The computer is really good at putting lots of relationships together and letting us see what is likely to happen over time or over space, given the system that we set up, given all these relationships that we set up. So computers are really, really useful for that, and we're lucky that we live in a time that we have powerful computers at our fingertips, but it doesn't necessarily do us much good in terms of using these computers to understand the systems that we're interested in understanding unless we can talk to the computer, unless we can get the computer to do what we want it to do. The process of talking to a computer is computer programming. It's understanding how a computer works and understanding how to get computers to do what you want it to do. So armed with some basic facility with computer programming, ecologists and natural resource professionals can really go a long way towards building an understanding of the systems that they're working with, an understanding of how everything gets put together and what the implications are for the future. In this course, we're going to spend a lot of time learning how to harness the power of computer programming and computer simulations for understanding and managing natural populations. And by the end of this class, you should all have the ability to harness computers to model a wild population of your choosing and to make management recommendations or conservation recommendations for that species. So that's where we're going. Let me just say one thing about modeling. This is a famous quote that by a famous statistician called George Box. He once said, "All models are wrong, but some are useful." And I think that's a good place to start when we talk about modeling, because really, when it comes down to it, models are simplifications of complex real-world systems. So in this class, don't be afraid to be wrong, because we're modelers and all models are wrong to some extent. So don't be afraid to be wrong. Like I said, this is all about learning by doing. So the more experience you get with modeling, the more you'll realize it is really not that difficult, and it's incredibly powerful and useful, and I hope you agree that it's fun. So let's get started. I will stop talking at this point and let's get modeling.